Hey guys, let's get into Voltaic. So what we've been talking about so far is the process of oxidation reduction. And oxidation reduction reactions transfer electrons. Well, that's actually how we do it. So any battery that you use is based on a redox reaction. So they have a lot of practical purpose. They're very useful to us. And so now we need to talk about the cells that are constructed to be able to get that energy that we can use and to measure how much energy there is transferred in that process. So we need to be able to talk about that structure. And that's what we do when we talk about voltaic, galvanic, electrolytic cells. And we'll talk about the difference between those. Okay. So a voltaic cell is built by having two beakers that are separated from each other. They are connected through metal wire. So that wire can be connected to an anode that's made of the metal in question, or it could just be platinum. So sometimes we use platinum for ions and things like that we need to be able to deal with. There's another connection between the two of them, and it's called the salt bridge. Now, a couple more things, and then I'll talk about the salt bridge. We always have our oxidation and our reduction separated, because if they're in the same place, we can't capture those electrons. They're not useful to us. By convention, we have our oxidation on the right, or on the left. And the way that I remember that is lose electrons, oxidize, Leo on the left. Reduction occurs at the cathode, red cat. So, and of course, reduction is gain, and gain electrons reduce. So I know that my electrons are going to travel from the left side to the right side. We can talk about some of the other things that we have here. We see that this is labeled as the anode because this is the oxidation. So that's my anode. We'll talk about that in a little bit. We see that this is a 1 molar ZnSO4 solution. That's where we get this Zn2+. And then this is a Zn solid metal. So we end up with Zn2+, and the 2 electrons that come out and go over here. We then come to our cathode. We'll talk about the definitions of cathodes in a few minutes. Cathode is where the reduction occurs, red cat. And my cathode is in here with a Cu2+ solution from 1 molar CuSO4. And then we have a copper electrode here, Cu. So that my Cu2+ plus 2 electrons goes to copper. So we're going to be taking away metal from that zinc and adding metal to the copper as we do this process. Okay, Leo's on the left, reduction's on the right. This anode goes with the oxidation. Both are vowels, anode, oxidation, and red cat. Cathode is the reduction. Now, voltaic cells are spontaneous reactions. We'll talk about what that means in a bit, but they're always spontaneous. Okay, so that's the definition of a voltaic cell. All right. So we have a number of different types of cells. One of the things that we need to be able to talk about is this salt bridge. I said that there was a salt bridge there. Now, this is where this gets funny. So my electrons are going from the anode to the cathode, right? So they're traveling through this wire so that we can measure them and or use them. But as that happens, I'm left with a positive charge on the left-hand side and a negative charge on the right-hand side. Let me ask you, ever walked up to a beaker and have it had a net charge? No, that doesn't happen. And so what needs to happen in order for these electrons to be transferred and this oxidation reduction to occur is we need to be able to transfer electrons, anions and cations, ion transfer. Sorry, that's the word I was struggling to find. So my salt bridge allows for, and the one that we show you here, this one says Cl minus in the salt bridge, and K plus is so K plus is my cation, Cl minus is my anion. We're typically filled with something that's very soluble, so it's common to have group 1 metals and nitrates or things like that. A Cl is not the best idea because if we're dealing with something that precipitates with Cl, that can be a problem. So it has to be something that's ionic. So it needs to be an ionic compound. It needs to dissociate so that we can move the cations and anions separately. And we need some way for them to move. Okay. So one of the ways that we do this is by using something like this to do it. We see this as a salt bridge. It has a liquid center, or it may be a gel. And then there's something to keep it from coming out. And that thing that keeps it from coming out is porous so that we can let the ions move through it, but not everything else. Okay. And so those ions will move as this becomes positive over here. Then we get Cl minus coming in here. As this becomes negative over here, we get the K plus coming to keep the electrical neutrality. So that's the key. Our salt bridge is to maintain electrical neutrality. Now, there are lots of things that can be used as salt bridges. So there's the one that we just saw where there's, this gel or liquid in this thing that has, porous ends so that we can move those electrons. You'll see that right here, there's some barrier, and it shows that anions and cations can move. This is very similar to what we have in the laboratory. So when we do this lab, we make it so that your cell is always going to work. And we don't want you to have to remember to put the salt bridge in because it won't work without the salt bridge. So we make the cells what we call a porous pot. And that pot can actually move ions through it. So that acts as your salt bridge. Okay. It's very similar to what you see here. Here we have a semi-permeable membrane, which allows those anions and cations to move through them. Okay. So that's what we're talking about in terms of making sure that we have electrical neutrality. Okay. That's what the salt bridge is for. Awesome. That's fun. Another thing that we can talk about, and we will need to talk about it for these labs, is something called cell notation. So I don't always want to have to draw the picture of the cell and yada, 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 yada. It's a lot to deal with. And there's a lot of information that's in there that really becomes important as we move forward. So we need to know what the metal is that's at the anode. We need to know what the metal that's at the cathode. We need to know the solution that's in the oxidation cell. We need to know the solution that's in the reduction cell. We need to know what those concentrations are. So those are things that we need to be able to deal with. And one of the ways that we do that is with a thing called a cell notation. And you'll see one right here. So we have Zn solid, and then this line going to Zn2 plus aqueous, 1 molar. And there's two lines, Cu2 plus aqueous, 1 molar, and a single line, Cu solid. Now that one line represents a phase boundary. So this is a solid, this is aqueous. There is a difference in phase, so there's a phase boundary there. Notice that there are two lines here. That indicates that there are two different cells, which has to be if we're going to get actual work out of this. Okay. We include what the metal is for the oxidation at the anode, which is here, and then the solution that it goes to, and this one goes from solid to ion. Okay. Lose electrons, oxidize, and then gain electrons, reduce. We go from the ion to the solid. Okay. We indicate the concentration. We'll get to why the concentration is important later, but we need to make sure that we include that if we know it. Okay. Now, if a gas is involved, we're not going to have the ability to use that gas as a solid electrode. It just doesn't work. They mentioned that we use platinum in that case. Platinum is an inert metal, so it can carry electrons without reacting with a bunch of stuff. When we do that, we have the platinum that we show as a phase boundary to the H2 gas, which is a phase boundary to the H plus aqueous. And so we have three of them instead of just the two. And the platinum is always on the outside. So if there's a third thing out there on either end, it's the material that's being used as the electrode, which is not part of the reaction. Okay, oxidation is always on the left. Lose electrons, oxidize. Go on the left. Oxidation is the anode. Reduction is always on the right. Gain electrons, reduce. Reduction on the right. Reduction is at the cathode. We get electrons coming from the plus charge since the current is defined as flowing from the opposite direction from the electrons. Yes. Physics and chemistry can't agree about how it works. Standard conditions for your cells are 1 molar or 1 atmosphere if we're talking about a gas. And then, of course, one of the questions you will get asked, that I will ask you, is what is the balanced chemical equation for this process? So we know we have zinc and we know we have copper. All right, fine. So I know that Zn is going to Zn2 plus 2e minus, because I need those electrons. And then the Cu2 plus is going to Cu solid, and I need 2 electrons there to make that work. So my overall reaction is going to be Zn plus Cu2 plus going to Zn2 plus Cu. Okay. Do I include any of the phases there? No, I didn't. Should I? Yeah, I probably should. Did I? No, I didn't. And that's because we really don't look at situations where they're in different phases. It's just not normally something that we do. We do need to make sure that if we're looking at a standard reduction potential, then it matches the information that we have. So if we have a phase, we need to check that. If we don't have a phase, then we can assume. It's a great thing that we do. So that's our cell notation. You'll need to be able to write a cell notation given a drawing like this. I'm not going to use that one because we didn't talk about it. And this is actually the one that we had the cell notation for before. So I know that I have Zn solid, phase boundary to Zn2 plus. That's aqueous. It's a 1.0 molar. That's right there. We then have our phase boundary to our Cu2 plus. Again, with 1.0 molar. And then phase boundary to the Cu solid. So I can look at that cell and say, okay, I know that the first thing I'm going to write is whatever this electrode is made out of. So that's the Zn. I know that the next thing I'm going to write is the ion that goes with that. So that's the Zn2 plus. Then I'm going to have another cell. And then I have my ion, the Cu2 plus, and the phase boundary to the cathode. So the electrode that's used there. Okay. Again, if this was a situation where I was looking at something against H2, which is a gas, we'd have PT, H2, gas, and we'd list the conditions for the gas, phase boundary, H plus, aqueous, 1.0 molar, and then our cell. So that's how we write that part of it. Okay. So that's what we're talking about there. So that's a cell notation. And we're going to be looking at cell notation when we talk about the lab that we're going to be doing, because we have things that we're going to need to deal with in terms of writing a cell notation, those strong things. You're going to get abstract, so we need to deal with them. So some examples. Copper solid goes to copper, and silver goes to silver solid. Okay. So again, we're looking at Cu S goes to Cu2 plus, and Ag plus goes to Ag solid. I know that this is a 1 electron process. I know that that's a 2 electron process. Lose electrons oxidized. This is my Leo. Gain electrons reduced. So this is my reduction. So oxidation, reduction. My overall reaction, I need 2 electrons for both of them. So I'm going to have to multiply this by 2. So I'm going to have Cu solid plus 2Ag plus goes to Cu2 plus 2Ag solid. That's how I get my overall reaction. And of course, the cell notation for that would be the Cu solid, and Cu2 plus, aqueous, aqueous thing. Aqueous. And we assume it's 1 molar. That's an atom, I swear. There's a phase boundary to the Ag plus, which is aqueous, 1 molar, and then the Ag solid. That's not written in one line. I apologize. But this is exactly what we're looking at right here. Notice that I didn't indicate here what the concentration was, but I wrote CONC so that I would know that I should include it. That's something that I do. It's not required, absolutely not required, but I like to always include something, and if I have a value, then I know to put it in there, and if I don't, then I just leave it as that. We can talk about magnesium solid going to magnesium, and iron 3 going to iron 2. My anode is Mg solid going to Mg2 plus, and that's lose electrons oxidize. My cathode, 2 Fe3 plus goes to 2 Fe2 plus. Gain electrons reduced, we gain 1 electron to go from 3 plus to 2 plus. My overall reaction, Mg solid plus 2 Fe3 plus goes to Mg2 plus 2 Fe2 plus. My cell notation here is going to be Mg solid goes to Mg2. That's aqueous. That's in contact or other cell with Fe3 plus and Fe2 plus because they're both aqueous. So we have the one with its concentration, comma the other with its concentration, and of course we always put the one that we are adding electrons to first. And then we have a phase boundary to the platinum. Okay, so that's another time when we do that. So this, again, we don't have a solid that's being dealt with here, so we need that platinum electron. If we know the concentrations, we want to put them in there. If we don't, we can leave them there. We can put it in or omit it. It's entirely up to you. And if the reaction occurs in basic medium, you must indicate that in your cell. So you either put it in the beakers that you're drawing or a note to show the OH minus in the beaker. Or if you're writing a cell notation and you have to do that, then you would go Cu solid plus not my overall equation, but that's not what I want. So Cu S Cu2 plus aqueous OH minus aqueous. And then my phase boundary to Ag plus and OH minus. And I'm just saying that it doesn't actually, that one won't be soluble. And then the Ag. So that's how we would indicate that. Since we don't normally include the OH minus, that's because the H plus is assumed. So we don't normally include it. But if you're in that, you want to either show it in your cell notation or in your drawing that you've got for this beaker. So if one of these was in an OH solution, OH minus, you can just indicate it. You need to show whether if that's what you see, then you need to show. Okay. Let's do some practice. Add ourselves a note page so that we can do this and pull up this slide so I can look at it. Hopefully you still have it to you so that you can see what it says. I'll try and to know from this. So it says chromium wire, 1 molar chromium chloride. I know it's a 3+ ion, so I know it's chromium chloride. Connected to copper wire, 1 molar copper chloride, and CuCl2. I happen to know that that's a 2+. Assume chromium is the anode. Okay. So the anode, lose electrons oxidized. That's the one that goes on the left. So this is the one that should be over here. Now, overall cell reaction, cell notation, half reaction, and half reaction. So I'm not asking you to draw me a picture. But I want to know what the overall cell cell reaction is. So I know that this is Cr solid, and it goes to Cr3 plus 3 electrons. I know that this is Cu2 plus 2 electrons going to Cu solid. Okay, so lose electrons, oxidize. I know that the chromium is the one that's losing the electrons. The other one, copper, gain electrons reduced because it's the one at the reduction occurs at the cathode. We assume chromium is the anode, so that's why they're in the end. My overall cell reaction, I'm going to have to multiply this by 2 and that 3. This feels familiar, doesn't it? 2 Cr solid plus 3 Cu2 plus goes to 2 Cr3 plus 3 Cu solid, and those electrons will cancel after we've done our happy math. So, and that's good because they need to. So that's my overall cell reaction. If that's my overall cell reaction, I know that my cell notation is going to be the Cr solid. Phase boundary is Cr3 plus. Yes, I have a 1 molar solution, 1.0 molar, because it said that in the thing, and I actually wrote it right here. That's phase boundary, and that goes to my Cu2 plus. That's aqueous, 1.0 molar, and Cu. So that's my cell notation. Now, my anode half reaction. Lose electrons, oxidize, happens at the anode. So this is the anode. So the oxidation. This is the cathode, reduction, and of course, red cat. So that's how I know that that's what that is. That's a lot. And remember, we talked about reduction, we talked about oxidation, we talked about reducing agents. So if this is my oxidation, this is my reducing agent. Don't forget it. This is my oxidizing agent. So all of those are things that we can still talk about. All of it is stuff that we can talk about. We will combine from the beginning, talking about what's the reduction, what's the oxidation, what's my overall balanced equation, what's my oxidizing agent, what's my reducing agent, what does my cell look like if you may have to draw it, what is my cell notation, which is the anode, which is the cathode, which direction do the electrons flow? Let's go from the left to the right if you put the anode on the left, that kind of stuff. So you'll see ad nauseum for this in the homework. The homework that you have goes from redox through voltaic cells and all of those things and the standard reduction potentials. And they ask you to use the same equations to do all of these things. You do them over and over and over and over again. The repetition is designed to make this so that you can do it without having to fall all over it. It is a lot to remember. So repetition is necessary to make this work. So here's repetition. Platinum metal is put into 1 molar platinum nitrate. Then connected to copper metal, 1 molar copper nitrate. And I haven't balanced that. Assume PT is the anode. Okay. PT. I know the charges on PT. My answer to that is but I may be able to find it. But I'm going to look at my exam here. I'll pull them up in just a second. First. Content. Course. So I'm pulling this up. So platinum is one of these things that's here in the middle. Okay. So it can have a large number of charges. So I'm going to look and see if I can find it in any interesting places. And a couple places that I can check. I can check my solubility rules to see if it's here in my solubility product constants. I don't see it there. I can look in my standard reduction potential tables to see if I see it here. And they don't. So at that point, I would go, I don't know what to do with it. And so you could ask me, what is it? And I'd say, oh, it can be platinum 2 or platinum 4. Okay. You use one of them. And again, on a test, if you didn't know, just pick one. Say, I didn't know what the charge was, so I said this is platinum 1 or platinum 2. As long as you indicate that that's the charge you are using, and then show me what you would do, that's what matters. Okay, I know that's okay. So platinum 2 is one of the ones that I had. So I'm going to say PT, NO3 and CU is a 2 plus. So I'm going to go there. Awesome. I know that this is what I asked myself. Assume platinum is the anode, so this is going to be my anode. So this is going to be electrons oxidize at the anode. It's going to be on the left. Cool. That's my overall cell notation. So my cell notation is going to be platinum solid in conjunction with platinum 2 plus aqueous. I know that this is 1 molar. I then have a phase boundary to the Cu2 plus, which is aqueous, which is 1 molar, and the Cu solid. That's my cell notation. My overall cell reaction. This is a 2 electron process, so I'm going from PT to PT2 plus 2E minus. This is going to be CUS going to CU2 plus 2E minus. Except it goes the other direction, so I know it's going from C. So I know that it's actually CU2 plus 2E minus 2 CUS, and I know that because it's at the cathode, so it has to go that direction. We'll talk about how we know that. So my overall reaction is going to be PT plus Cu2 plus going to PT2 plus CUS. And of course, when I'm trying to write an overall cell reaction, I can see that this is what I start with, this PT right here. This is what I start with. And this is the metal that I end with. Over here is CUS. That's the metal that I end with. So I know that this is a reactant. This is a reactant. And this is a product, PT2 plus, and my other product is a CUS. Okay. So that's how I know that that's where that's all going. My anode half reaction is this one right here. I also know that this is the oxidation. This is my cathode. This is reduction. And of course, oxidation agent, reducing agent. Really handwriting, but that's so that's what we're talking about. Are there any questions about any? Okay, again, I hope not. Now that is the end of the material that we're going to be talking about today. We're now going to go into a brief description of experiments 6 and 7. We'll do a detailed experimental lecture for both 6, 7, and 8 this week, because all 3 of them are this week. So you'll get a lab lecture for each of those. But take a break here and get some of this. and stop this recording so that we can get this posted. Thanks, guys.